Hey, Physics 30, I'm going Physics 30. So I'm going to go over this special question document that I created. A bunch of questions that kind of popped out of, I don't know exactly how long ago, 10 years ago. They just released a bunch of these kind of specialist questions that they could ask, right? So we're going to go over them, and if I feel ever so inclined, maybe I'll put little links in the doobly-doo, timestamps in the doobly-doo. You can jump around if you need to, but that's if I feel like it. So let's get started here. All right, so in these first few questions here, there's a couple of things that I want to point out. Is that I haven't seen it in a very long time. Actually, I don't know if I've ever seen it ever actually in a real exam, but it doesn't mean that they can't do it because they released these, so hopefully teachers will be looking at them and preparing for it, that you might need to actually measure on the diagram. So you have to pull out a ruler and actually measure, physically measure, like how far certain objects have moved here, right? So both horizontally and vertical. You can see at the bottom here, it very specifically says you will want to make measurements on this diagram. So that's going to be very important. So sometimes they just say the diagram is not to scale, and that means, okay, don't trust the diagram scale. You can't actually physically measure anything on it. But if they say this, you will want to make your measurements on this diagram, it'll mean you actually have to measure certain things. So I'm going to pull out my ruler, right? And I'm going to measure on a physical piece of paper here that you should have in front of you as well, how large certain distances are. And I may not use them all, right? So some distance you might want the total distance between the plates. Maybe that's going to help us find like the electrical field if we need to calculate that electrical field. So let me just quickly measure that. 1.8. So that's 1.8 centimeters there. Okay. Some things you may want to know is how far vertically the electron or whatever particle this is has traveled here. And I think when we did this in class, it was 1.1. Yep, there's 1.1 centimeters. You might need to know how far horizontally the object has traveled as well. So in this case, 4.3. So there are some measurements that you might want to take, right? In a future question, we might have to actually pull out a protractor and actually measure those distances. So these are the ones I'm going to take. These are probably the most common ones if you're going to measure on a diagram what you might need. And then from there, we can try to answer the question. So this would be a very big numerical response question. You might take a lot of steps to do this. Not a sponsor. So what we're going to do, in this case, let's kind of decode what we have to do. We need to determine the electric field, which is newtons per coulomb, not the electric force, but the electric field in this region, right? So to find the electrical field, now what we have to do is kind of look at the formula sheets that are behind my head here and think about which formulas we're going to need to determine the electric field and how are we going to determine it. And as you think about this question, because this is a big question, there's most likely going to be another question after it that talks about these physics principles. Now the physics principles are located on your formula sheet. Let's see if I can load up my formula sheet here really quickly. Let's see if I have one. This is demo, yep. So they're located on our formula sheet. Oh, so that loads up right here. At the bottom, underneath the constants, right? So there's your constants up there. And there's a bunch of these physics principles underneath it. And here we're going to want to know, as we do the question, which physics principles do we use as we go through this question, right? Do we ever use uniform motion? Do we use accelerated motion? Now there's indicators that I talked about in class about when we use these, right? So like the first one here, let me just draw them out. The first one, if I ever use where A is equal to 0, such as V is equal to D over T, then I'm using the uniform motion stuff. So if I ever use D over T is equal to V, that's uniform motion. If I use any of those other 5 formulas, if A is not equal to 0, and I calculate F net by going M times A, or I have to find A somehow, right? You have to find A using like any of those other 5 formulas up there, then that's going to be accelerated motion. Uniform circular motion, that's if you have to calculate like VC using like 2 pi r over t. You don't see that one in physics 20 that often. Or AC, right? V squared over r, or the other one, 4 pi squared r over t squared. Or maybe just finding FC, m times AC, right? So if you use any of those, you've got circular motion. Now work energy theorem, that's like if you calculate work, which is equal to force times distance, which is also equal to the change of EP plus the change of EK, right? Because work is the change of energy. So if you calculate change of energy anywhere, right, and this change of total energy, mechanical energy, then you're calculating the work energy theorem, right? Conservation of momentum, that's when you go like V before is equal to P, the momentum, sorry, before is equal to the momentum after. And you could also think of this as impulse. If the impulse of one object is equal to the negative impulse of the other object. Because if one momentum goes up, the other has to go down, which is how it works out. Conservation of energy, this is like thinking kind of like momentum here. What's the energy before and how does it compare to the energy after? Mass energy, that's if you ever use E is equal to mc squared, right? They put a bunch of deltas in the formula, do they? Yeah, they are. But essentially E is equal to mc squared. Conservation of charge and nucleons, these guys are kind of tied together. Like conservation of charge could just be you touch 2 objects together and you separate them. Okay, so that's just calculating the new charge if I touch 2 and separate them. Add them together, divide by 2, add them together, that kind of thing. Or when you're balancing out a nuclear reaction, and you can just make one up here, you're balancing out the bottom numbers. So like when you balance out, I don't know what element this is, and it becomes like element Y in like a beta negative or something. How do you know this bottom number is 27 in this new element here, right? So using these bottom numbers, that's charge, right? And the top numbers, that's nucleons, which makes kind of sense when you're doing this, right? And wave-particle duality, if you ever use P is equal to H over lambda, or lambda is equal to H over P, then you know you use one of those wave-particle duality stuff. That's just Compton and de Broglie put together there. So when we're doing this question, we got to be thinking about that. Okay, so let's close this down for now. Let's go back to the question we were doing. Okay, so what are we doing here? We're trying to find electric field. So looking at our formulas, I have 2 ways to find electrical field. I can find electrical field using the voltage and the distance. We've got the distance here, but I don't have the voltage. Now, if I want to find the voltage, I can find the change of energy and use that with the distance to find the voltage, and then I can use that. Yeah, I could do that, but maybe that's not the way I want to approach this question. Another way to find the electrical field, I'm going to work my way backwards here, is to find this electrical field. I'll have to put it down here. I may want to find what the force is on that electron. The force is acting on this electron in the vertical direction. So I'm going to have to find some things about the vertical direction, right? So if I want to find that force, divided by Q, and I get my electrical field. So to find the force, I'm going to probably want to find the acceleration, because this force is technically equal to my F net, I guess. Because maybe there's a little Fg, but Fg is small enough that I can almost say it's 0. It's small. It's not complete 0, but it's negligible at this point. So we can say it's small enough, right? So maybe to find F net, I'm going to have to determine mass times acceleration. Okay. Well, I know the mass. Okay, that's good. Maybe I have to find the acceleration. Remember, the acceleration is in the vertical section there. So to find that out, maybe I have to go to create a T-chart here. Okay. So I'm going to find my acceleration. What do we know? So in the vertical section, we know the distance traveled is 1.1 centimeters. We know the initial vertical velocity is 0. And to find acceleration, I'm going to have to know time. So to find the time, I'm going to go to the horizontal section. I'm going to scroll up here just a bit more. So the horizontal section, we can find time because we know the distance it travels here is 4.3 centimeters. And its horizontal speed is 450,000 meters per second. So we can use d over t to solve for time. All right, so we pull out a calculator, and we can start doing this question. Okay. 4.3 centimeters. So I'm going to just change it to meters, divided by 450,000, and we get 9.55, bunch of decimals, times 10 to the negative 8 seconds. So I'm going to take that up here. 9.55 times 10 to the negative 8 seconds. And we're going to use that to help us find the acceleration. So our acceleration, I'm going to use the d is equal to v. I'm going to run out of space here, but d is equal to vit plus 1/2 at squared. Right? Now vit equal to 0 because vi is equal to 0, and I can rearrange this. So it's going to be 2d divided by t squared. All right, and I can find out what a is. So I got the t squared in my calculator. So 2 times the d divided by t squared. So I get an acceleration here. I wonder if I can move all this stuff down. Oh, yeah, maybe I can. Let's put it right about there. Okay. So I get an acceleration of 2.409 times 10 to the 12 meters per second squared. All right, so it's quite a big acceleration, but it's such a small time frame, so it's not going to go super fast. All right, then I'm going to say times by the mass, which is an electron. So I can find out that force is 2.1949 times 10 to the negative 18 newtons. And then that's going to be my Fe, okay? And that's going to, and then I could just divide by Q. And this is an electron, so 1.6 times 10 to the negative 19. So I get 13.7 newtons per coulomb. There you go. Cool. And there you go. So that's my answer. So, bada boom, bada bing. Big question. Okay, so now, how did we get there, right? So the first thing we did, I look over here, the very first thing we did over here was calculate the time using v is equal to d over t. So the first thing I did was use, if I go back to my stuff, uniform motion. So that's 0. So I'm going to put a 0 in this first spot. That's the very first thing I did, because I used v is equal to d over t. Technically, I used d over v to solve for time, right? The second thing I did was calculate the acceleration and then calculate the F net. So because of that, that's going to be number 1. So I'm going to put a 1 in that spot, right? Because I used F net is equal to m times a. There we go. So you'll see a few of these questions. Okay, you'll see at least, hopefully, I want to say hopefully, but you will see most likely one of these questions on the test. Right? One of these big ones, probably the last one on the exam. Bunch of different steps to it. You can see I just crammed in that little corner. Hopefully they give you more space. I guess I could have done down here. Right? So I could have spaced this out a little bit better. So if I could have put, I won't put that there. I could have put this stuff down here. And I could have put this stuff here in a different area too, right? Yeah, a little bit nicer. Right about there. Yeah. Okay, there we go. All right, this is a good question. I kind of like this one. It talks about like measurements and how would you set up an apparatus to get a focused image. So very key, it has to be focused. So that means everything's got to be in the right position. And you can see from the picture, there is there's the measurements here. So 20 in the middle. This is like 5 centimeters over here, right? And over here, this is 35 centimeters. So everything's like 15 centimeters away from each other, right? Or 15 whatever. I'm assuming that's centimeters down there, right? And then we want a real image. And you want a real image because that's pretty much the only way you can actually get a focused image on a screen, right? You want it on a screen, so you're going to want a real image. So you got to make sure it's on the correct side of the lens or mirror, right? So now this one here, it says it's not drawn to scale, but we can use this little measurement down here to help us figure this out. We want to create this apparatus, and there's going to be multiple different ways to do this. I'm going to do it one way, but you can always just flip the whole thing right over. Put the lens on one side, or the mirror on one side, or put the mirror on the other side. So, there's two ways to do this. Okay, so we want to create a real focused image. So I can create that with a lens, or I can create that with a mirror. So first things first, very key, it says it's real, diverging and convex and plane mirrors will never create a real image. They always create virtual images. These are always virtual. It's just the thing we know about these types. So it has to either be a converging mirror, or lens, sorry, or a concave mirror. Okay. Now, if I want an image too, I'm not going to use diffraction gratings or dual slits. That just creates interference patterns. So this one creates an image, right? It's just no image in these ones. So I don't see why we would want this here. Right? If I wanted a pattern, like an interference pattern, yeah, go ahead, put those down. Now I can either use a laser or a candle, doesn't matter. Yeah, it depends on the lasers is set up, but it really doesn't matter about that. Okay, so what I'm going to do is I'm going to maybe test it out. So let's say I did 2, right? So I'm going to put 2 in here, and you're going to put like a light source somewhere. So let's say I put the candle here. So here's my candle. Right. Okay. I'm going to put, let's say I'm going to put the lens in this spot here. So I'll use my converging lens at this point. And then I'm going to put the screen over here. This is where the observer is. Right. So you would be over here observing what's happening. So technically this would be real, right? Because it's on that same side as the observer. But you have to make sure, the key is it has to be focused. Is this going to cause a focused image? So our focal length here is going to be, because we picked converging or concave, is going to be a positive 10, right? Because of that, we're not using any of those negative ones. And we just have to make sure the distance of the image ends up in the right spot. Okay? So let's do a little mathematics here and see if this actually kind of works out. So we're going to go 1 over f is equal to 1 over do plus 1 over di, and we're going to solve for 1 over di, right? Just to make sure you get in the right spot. So this is how I kind of have it set up for this picture. So this distance right now that we have for do, that's 15 centimeters. So I'm going to put 1 over 10 plus, or is equal to 1 over 15, and I want to find out what di is. So if I rearrange this and I get di, I would get di 1 over 10 minus 1 over 15. Make sure to take the inverse of that. How does that work on this calculator? No, let's go with that. I get 30. It's a positive 30. So we get a real image, positive 30 centimeters. So this is real, so a check mark, but it's got to be at 30 centimeters for it to be focused. So this is not going to work, right? I had to make sure it's at 30 centimeters, right? So that's not going to work. Like I can't do it. Plus, location Z is not at the right spot. Location Z is at 15 centimeters. So for this to work, location Z has to be at 30 centimeters. It's got to be twice as far as it is right now. So it doesn't work. So based on what we concluded here, that doesn't work here. So I'm going to have to redraw what I think this picture is going to look like here. Okay, so let's do this all over again. So what we can do now, let's put the mirror here. All right, so there's my mirror. Nice concave mirror. I can't be behind the mirror this time, so I'm going to have to be over here somewhere. All right. That's a funny looking person. All right. So I'm going to be there. I'm going to put the, I don't know, if I put the object here. So again, I put the candle in this spot. Right. And that's going to be 15 centimeters away. 15 centimeters away. 30 centimeters. That means I just had to put the thing over here. So this is going to work now if I put it here, because that is 30 centimeters away. Right. So my DI is 30 centimeters. This is 30 centimeters to get my focus image. So this is a good setup. All right. So it'll be nice if on X here, I put the screen on X. So I'll put 9 there. On Y, I put a candle or the other one. So I can put 1 or 0 in that spot. Doesn't really matter which one. And on Z, I put the proper mirror there. I put 4. Right? I can always flip it around. Right? I could put the mirror on the other side. And also what's nice about this is I can flip where the candle and the screen are, and they'll work as well. But this is one setup. And there we go. All right. Lots and lots of different things you can do here, but that's one of it I did. Okay, so this one here, we're going to have to do some measurements on this picture. We're going to determine the index of refraction of the second medium, but based on the measurements that we picked. Okay, so we're going to pull out our protractors here, and we're going to measure the appropriate angle. So I got my picture in front of me. So the first angle I'm going to measure is we always want to measure towards the normal line. So this angle here is one I want to measure, and this angle here is the other one I want to measure. So I'm going to measure those two. One's called the incident. So this one down here we call theta I for incident, and this one up here is theta refracted. I'll just call it theta R for now. Okay, so I'm going to measure those. So they would expect you to measure them to the nearest degree. So based on my picture here, my bald spot, this first angle looks like 39 degrees. Not quite exactly 40, but 39 degrees. So that's 39 down there. And then I'm going to pull out my protractor again. Just flip it around and measure this upper angle here. Make sure that line's right on that center line there. And I got about 32 degrees there, 32. So not too much of a change. So I just want to double check and make my measurements are correct there. Making sure I put the dots on the right spot. And it's like so close to being 40 degrees. I think it's close to the 39, but 40 degrees probably would actually work here for this. They would always give it a little bit of wiggle room. Like if the angle is not exactly what it should be, then it could probably be one or the other. But these are the two measurements I got. Yeah, and the one above here. Just a bit more. Yeah, cool. All right, so we're going to use this to calculate this index of refraction up here. We don't know what this one is, so this NR that we're trying to find, we know this one down here is 1.33 because they say it down the bottom. All right, so I set my Snell's law equation here, so NR over NI. It could be 1 over 2, but what's very important is that if you put R on the top there, when you go sine theta, you want to put R on the bottom and I on the top. So it's got to be kind of reversed there. Right? So I can put 1.33 here in the I spot. We have an angle of 39 here on the top and 32 on the bottom. Making sure our calculator is in degree mode. It will very specifically say in the very first question it needs it, unless they forget this here for some reason. They'll just say, make sure your calculator is in degree mode. And then type everything out. And we get 2.32. Now I know we kind of designed it right because it is bending towards the normal, which means it's slowing down. And if it's slowing down, that means the index of refraction has got to be bigger than the previous one. So it's 1.33 before. It's still going slow, but then it slows down even more. So this 2.32 looks pretty good. So I think that's a good answer to put there. Cool. Okay. Positive charged ions are traveling through the region in a perpendicular electric and magnetic field. So there's two fields there. And it's going undeflected. All right, that's easy enough. Now we know it's going undeflected because there must be two forces. So this is a positively charged ion. So it's coming in as positively charged. So based on that, there's a force pulling it upwards. A positive and negative are going to attract each other. So that means it must be the electric force. And if it's being undeflected, that means the magnetic force must be going the other way. Just the way it is. All right? So let's basically see what it says. Direction of the electric force upwards. So that is 5. Okay. The direction of the electric field. Okay, so electric field, remember field is the direction a positive charge would go. So the field is going from a positive to negative here. So yeah, so that would be also 5 because it's also a positive charge. Yeah. Direction of the magnetic force would be 6, right? So that's 6 right there. That's going downwards. And let's pick a different color, purple. Direction of the magnetic field. Okay, so what's going to cause that force? So we're going to have to pull out our hand, very specifically our right hand, and we're going to put it in the proper direction. So we're going to make sure our thumb is going in the right direction here. Is that my right hand to you? I can't tell. Put my thumb in the right direction. I got to make sure my palm is facing downwards because that's the direction the force is going. And based on how you orient your hands, it's coming straight at me, right? So it's technically coming out of the page to me, right? Because my fingers are coming out of the page, right? So that's to create this force downwards, there must be a magnetic force or magnetic field out of the page here to create the force downwards. Remember, I'm using my right hand here. So that's out of the page. That's going to be 0. There you go. Make sure this is my right hand. All right. I don't know if I can draw this out, but we have our thumb here coming outwards here. We have, this is my three-dimensional hand here. All right. That's the back of my hand. All right. So on my force going down, right? That's my force. This is the direction the particle is traveling, right? So this is my, yeah, that's my right hand downwards. And then my fingers here are kind of out of the page. That's the magnetic field that we're looking for. Cool. Not a very good picture there. Okay. I like that long arrow there. Kind of confusing. Okay, let's try out the next question. I remember this question. So during the contact of this car, remember, they're in contact. So when these cars are in contact with each other, this is during the collision part of it. Cart 1 and cart 2 are going to be pushing on each other. So cart 1 hits into cart 2 and pushes, that's weird, okay, pushes with this force, I don't know, this action force, which is cart like 1 on 2, right? And then cart 2 pushes back because it doesn't want to move, right? That's Newton's first law. But Newton's third law says that it's going to push back with the same force, but in opposite direction. Okay, so now we know this is just Newton's third law. Third law, right? Now we know they're interacting with each other, same force, but opposite directions. And if we're talking about impulse, where's the impulse here? Remember, impulse is calculated by going force times time. So if they have the same magnitude of force, but in opposite directions, and they're interacting for the same amount of time, right? So they're colliding with each other, and they're interacting for the same amount of time, they wouldn't make any sense if one pushed longer than the other, then these are both the same but in opposite directions. So this is the same time, but opposite direction. So it makes sense it's going to be A. The same magnitude lines, the same length, but in opposite directions. Okay, that's a fun question. Negatively charged rod is brought in contact with initially a neutral sphere. The rod is removed, and the resulting net charge result there. Okay. Now you notice that the charge didn't spread out, right? The charge kind of grouped together there, and the reason it just kind of grouped together is because the charge can't go anywhere. It's on this weird sphere that doesn't allow it to move, right? If it was a conductor, right? So I'm just going to mention this, like I'll just draw it. Like the answer is it's an insulator, right? If it was a conductor, what a conductor would look like afterwards is that all the charge, the four charges, would spread out as much as possible, right? So that's the difference between the two. Like they're trying to mention that this charges haven't spread out. They kind of grouped together in this little area right here. Right? They grouped, right? They haven't spread out, not spread, right? And because of that, we got an insulator. So we're going to cross off these conductor ones. And the process, because it came in contact with it, right? Contact, conduction, right? So it's got to be one of those two. So last one. So conduction and then insulator. Okay, so this is just your Lenz's law, right? We got this magnet coming down here. Based on Lenz's law, it's going to take some of that kinetic energy and produce some electrical energy, but in the turn, because the only way you can take the kinetic energy is to try to slow it down, so they're going to try to slow it down by pushing back at it. So there's going to be a south at the top and a north to try to push back, right? To push back. Lenz's law, right? So because of that, I'm going to take my left hand, and then I think we want to figure out which way the electron's moving. So we take our left hand, we put our thumb in the direction where the north is. If it's south is on the top to push it back, then north must be on the bottom, right? So put my thumb in that direction, and then my fingers are going to wrap around the picture. Watch out, my hand. This is all reversed here, so I'm just going to put my hand off the screen here. So I'm going to put my thumb downwards, right? And then thumb down. I don't know how I would do this. Thumb down. And my fingers are going to wrap around right? This is the front of my hand here. My fingers are going to wrap around. So this is where the north is down here. And this is the direction the electrons are going to flow, right? So they're going to kind of flow in that direction. So technically, it's kind of crappy picture I drew there, but the electrons are going to flow in this direction here. Right, so maybe I should redraw this hand a little bit differently, more of a top-down picture. So there's my thumb, right? And then here's my fingers up here, right? All right, and then so north down, and then my electrons are going to flow in that direction there. Okay, north down. You wouldn't be able to do this, like see your hand that way, but if someone was looking at your hand, that's what it would look like. Okay. That's my left hand. Yeah, it's a left hand. It's just strange looking left hand. All right. Put some fingernails on there so you can see some fingernails. There you go. That's what I thought. Okay. So the electrons are going to flow from Y to X. So I'll cross off these ones. And compared to x, the nature of y will be relatively positive because all the electrons are going to x, so x would be negative. But compared to x, what would y be? Y would be positive. There you go. So this side would become negatively charged. This side would become positively charged. The positives are not going to move that direction. Only the negatives are going to move, but it's going to kind of expose those positives. Yeah. Positively charged sphere suspended at this. Again, this is going to be a Lenz's law question. You got the south going in. So what's going to want to do is going to want to push back, right? It doesn't want that to happen. It's Lenz's law. So to push back, there's got to be a south here and a north here. So we're going to use our hand rule. I'm going to put my thumb in the direction of the north. And then my fingers, this is the back of my hand this time, right? So my fingers are going to go the other direction, right? So my fingers are that way, and this is the north side. I don't know why I put a thumb there. This is my second rule. So put a north here. That's my fingernail, thumbnail there. This is the back of my hand. So my finger's going that way. So based on this picture, my electrons are going up the top and down the back, right? Based on how my hand is wrapped. So the electrons are going to go this way. The electrons are going to go this way. The electrons are going to go this way, and they're going to pile up here. And that's going to pull the positive over towards it. So this ball is going to move towards plate 2. And there we go. Because they're going to attract. All right, so this is going to have an electric force in that direction. It's a really bad picture of the back of my hand there. I'm only halfway, 40 minutes into this question. Well, hopefully we keep on going here. Girl is 22 centimeters tall in front of a particular mirror. Her virtual image in the mirror is upright, and 40 centimeters tall. So it's being diminished and it's virtual. So very key, it's being diminished and it's virtual and it's upright. All those characteristics say that this must be a convex. So they all kind of collide together. It's virtual. It's upright. It's smaller, right? So this is being diminished. Diminished. Or whatever word they want to use at that point to represent smaller. Because of that, it's got to be a convex. Right? In a concave one, if it was virtual, it would be enlarged. It's like a makeup mirror. I take that big mirror and I put it right in front of you. It's got this huge face. It's upright, right? And virtual, but it's enlarged. So concave lenses would do that. What else? And the girl's image is located how far? So that's DI. Okay? So let's try it out. Yeah, okay. There's a couple other ways you could do this mathematically. If I wanted to, I can try to prove that's convex. I'm just kind of looking at what we have to do here. So my magnification, which is going to be negative DI over DO, is equal to, and then over here, we have HI, which is 54 centimeters, and we have that one, okay? So we have those two numbers. It's upright, so upright, that means this is a positive number. This is also a positive number. All right, so upright, that's gonna be important. All right, upright, magnification is that. DI would be negative. Yeah, okay, so we got DI as being negative. And we can figure out exactly what it is. Actually, I don't know if I can figure out particularly. It stands 40 centimeters in front. So we know DO, we can find DI. And, then we can set the math here. We just do the math. Okay, and so we know DO is 40 centimeters. We just have to find what DI is. This doesn't seem too bad. I think it would be hard to maybe find out more things about it. But this is to find out what the other one is. So this is easy enough. Cross, multiply, divide. Cross, multiply, and divide. You get 17.7. Technically negative, because of the negative part there. So negative 17.7 centimeters. So I know it has to be 18 centimeters. So I'm just going to come back. It's going to be A. But then to figure out if it's going to be convex or concave, I can find out what F is. So I'm going to go 1 over 40. That's always a positive. And then 1 over negative 17.7-ish centimeters. You do the math here. So 1 over 40, kind of minus, but plus 1 over negative, this answer that we just had here. Oh, we got a negative answer. We flip it over, still negative. So we get F to be negative 31.8 centimeters. So this means convex, right? But you already kind of knew it. Okay. So in an investigation, a group of students measure an object to be 10 centimeters tall. They place the object 3.2 centimeters in front of a thin lens. They were unable to locate a real focused image. They draw the ray diagram and they realize that it was supposed to be a virtual image on the same side of the lens as the object. Make sense? It's 1.3 times larger than the object, but we don't know if it's inverted or anything, but we do know it's virtual. Oh, it's taller. So it can't be can't be diverging, because remember, in diverging it's always diminished, right? So this is larger, right? It's larger. It's not going to be diverging. It's got to be converging, right? Just how it works out, right? But there are ways to find that out, right? It's virtual. It's larger. Oh, it doesn't matter say if it's going to be upside down or not. Most of the time when we did virtual, it's always going to be upright. But that's okay. We don't necessarily have to worry about that. We just have to figure out what's the focal length here. Yeah, just based on that. Based on I know that's larger, it has to be converging. Remember the diverging mirror, the convex mirror and the diverging lens have the same mathematics, and they always end up being the same. Virtual, diminished, and upright, right? Yeah. Yeah, cool. Yeah, so let's do the math on this one now. I wonder if you can figure this any other way. It's 1.3 times larger. Find out what DO, and we can find out what DI is, but it's either positive or negative. Oh, but it has to be negative. Right, DI has to be a negative number because it's virtual. That means the 1.3. Yeah, okay. Kind of weird logic here, but it's virtual, so DI must be negative, right? So I'm going to think about this in that situation. So if I were to write out the math and say the magnification, and I don't know if this is positive or negative 1.3 yet. Like, I don't know this, right? But if I go negative DI over DO, and DO, remember DO is always going to be positive. I just had to make sure which type, positive or negative, would end up having a negative DI. So I can't have a negative 1.3 because that would be two negatives would make a positive. So this has to be positive to make this work out nicely. Give me that negative DI. So DI would be 3.2 times 1.3, but negative, so it's going to be negative 4.16 centimeters. If you put the other magnification with a negative on it, saying that's inverted, I would have a positive DI, that'd be a real then they would have found it. It says it's virtual. So this is virtual. That's very important. Then I can use that to figure out what the focal length is. Go 1 over f is equal to 1 over do plus 1 over negative 4.16. And I can figure out what f is. Okay. Hopefully get a positive number. 1 point plus 1 over. I think I have this answer in my calculator. I'm just double check here. Yeah, and then 1 over that answer. Gotta flip it over. Okay, so I get 13.86. Positive 13.86 centimeters, which is positive 14. So, there we go. All right, we knew it was converging already, but this also confirms converging. Cool. So this is per unit kilogram, so per kilogram, or 1 kilogram, based on these two reactions, which one's going to have more? Okay, first of all, which one's the fission reaction? The fission reaction is reaction 2, right? Because it's taking a bigger and turning into a smaller. The top one's a fusion. And reaction 1 will release more because it is fusion. Fusion is always more. Fusion. Oh my lord. Fusion releases. Oh my lord, what am I spelling here? Releases more. Right. Cool. The mass equivalents released by the burning uranium. Do we have the information for this? Oh, we have this. 1 kilogram of uranium burns that. This much energy is released. So we're just trying to find the equivalence of that energy. So I want to know what the mass equivalence of that energy is. So this is going to be E is equal to mc squared. So I'm just going to rearrange it from m. So I've got E divided by c squared. And they give us the E in joules already, right? Yeah, that's good. 6.11 times 10 to the 13 joules. And I'm going to divide by c squared. Okay, sounds good. Let's do that. So we get 6.79 times 10 to the negative 4 kilograms. So they are giving kind of hints here, like this is a single digit, right? So if you got 2 digits or no digit at all, then we probably did something wrong, right? Yeah, make sure it's rounded properly, and we got 6.794. Right? Oh, it's de Broglie stuff, the wavelength of solar wind. So this is de Broglie's wave and particle duality stuff here. So to use this formula, we are going to have to find the momentum of this particle, and that's pretty easy. Momentum of massed particles is m times v. There's no real other way to do it, right? You can't use the PC formula. So that E is equal to PC formula only works for massless particles. Massless particles. I know I spelled that wrong. Only. All right? Let me just fix that up there. All right? Massless particles only, right? So I can't use that one. So because this has mass, it's an electron, I can use m times v. So this shouldn't be doing, I'm not bothered writing this out. Just make sure you use the proper H, right? The H you're going to have to use is the 6.63 version for the mass of an electron. Sorry, I'm getting blinded by the light here. And the speed. 1.8. Maybe that's a bit nanometers sign, but 1.8. Yeah, 1.8 nanometers. Cool. Okay. Classical wave theory and quantum mechanics make different predictions about certain things. Like some of these are going to be wrong, right? So usually the classical ones are the wrong ones. Okay, let's see what it says. The low intensity electromagnetic radiation on a long surface for a long time will cause photon emissions. That's false, right? Einstein said and proved it. It's instantaneous. A photon hits it, electron pops out. And if the energy of the photon, the energy of the light is not enough, it doesn't matter how long you put it on there, the electrons are not going to pop out, right? So this is the old classical theory. It's wrong, right? So this is wrong, right? Let's go down here, wrong. Okay, high intensity photons will not cause the photon emission unless the frequency is greater than the threshold frequency. That's true. So that's a true statement, right? Got to bypass that threshold frequency, have enough energy, and that is quantum mechanics. Okay, true. The energy of the emitted photon will increase if the intensity increases. Now, intensity, remember, is how many photons, not how much energy the photon has. Remember, it's a one-to-one thing. So this is false, right? Because intensity doesn't change the energy of the photon, which means it doesn't change the energy of the electrons. It just changes how many electrons there are. So that's a false statement. So that's going to be 3, right? And then it makes sense. The last one's going to be true. Let me double check. Is independent, so it doesn't actually matter. Yep, that's true. So that would be 4 there. Oh, hope I'm not missing anything. Just double check my emails here. Just 1 second. Usually I pause the screen when I do this, but I'm not going to do it this time. Oh yeah, there's water leaks everywhere. Okay, cool. Compton scattering. It's being deflected back at an angle. This. The wavelength of what? What have we doing in prediction? Which of the following scattered photon to the incident photon? So the scattered photon would have a longer wavelength, right? It's not going to have a higher frequency because higher frequency means there's more energy, but it should have less energy. So that means it's got to be one of these other two. It has a longer wavelength, so that's good, okay? And the photon is not going to go any slower, right? Remember, photons travel at the speed of light. They don't go any slower, right? They can't go slower than they were before. So based on that, just got to be B. Not even have to look at all this numbers and stuff. If you want to calculate it, you can. Calculate the momentum and do all that stuff, but I'm not going to do that. One of these questions, when they give you all these numbers, you don't have to worry about it. But we still have to do some math down here. So the wavelength of the scattered photons, we just had to figure out what that is. So they don't give us the initial wavelength, but we can figure that out. I'm going to write that up here. Because if I'm going to find the wavelength of the scattered one, I have to know what the initial wavelength is. So what is my initial wavelength? I have the energy. So I'm going to go E is equal to HC over lambda. Lambda is equal to HC over E. If I can find my initial energy, I can find my initial wavelength. So I'm just going to quickly calculate this. They gave me joules, so I'm just going to use the joule number. Remember, you're trying to use as little constant as possible to avoid rounding errors. Okay, so this wavelength is 9.945 times 10 to the negative 12 meters. That's my initial. That's not my final. So this one down here is I want to find what the final wavelength is. So what is my final? That's what we're looking for. But to do that, I need to find the change. How much does it change by? So Compton, can't see it up there, but it's over there, says that the change can be calculated by going H over MC. This is whatever it hits. If it doesn't mention what it hits, oh, right there, scattered electron. So it's scattered. It says it's at a carbon target, but it hits the electron. So it scatters off an electron. So that electron mass is going to be used. Okay? And then we're going to go 1 minus cos theta. Like 99% of the time it's going to be electron. So just assume it's electron and probably be safe. Again, use the Joule version of H there. And I'm just going to quickly type it in. Make sure your calculator is in degree mode. And this calculator is in radian mode. Oh, man. Do I have to go back now? Why is this calculator in radian mode? Oh. Okay, I have to go back. Because I remember I did a question up here that involved angles. Now I have to double check it. It's all messed up now. Poop. So that's not right. Let me erase this. Oh, I can't erase that for some reason. Why can't I erase that? Go away. Can I just scribble it out? No, apparently it won't let me erase it. Let's go white and a big marker here. Okay. Let's redo this question, okay? So, who took my calculator and changed the mode of the calculator? Why would you do that to me? That sucks. 1.33 times sine 39 divided by sine 32. There we go. It's a bigger number, but not as big as it was before. There we go. What is happening here? Go away. All right? Okay. Now this is going to work. 1.58. Someone borrowed my calculator for a test, and they changed it. Wow. Do that. Okay, let's go back down here. Okay, so make sure your calculator is in degree mode. All right? 6.63 times 10 to the negative 34 divided by the mass of an electron times the speed of light times 1 minus cos 133. Yeah. So let me do that again. So 1 plus, 1 minus, 1 minus. Maybe I put plus by accident in my calculator. Divided by 9.11 times 10 to the negative 31 times the speed of light times 1 minus cos 133. There we go. Got a positive number this time. You can't get a negative change. Remember, the wavelength will always go up. All right? So this should be always a positive number. So there is my change. Remember, this is equal to final minus initial. That's what my change is equal to. So my final is equal to my change plus my initial. And that's going to end up being this plus this number that I have up here. 9.945 times 10 to the negative 12. It's a significant change here. It's going to be 1.4 times 10 to the negative 11 meters. So I'd probably put 1411 in that spot there. Whew. Which of the following best represents the predicted path of the scattered electron? Okay, so let's see. The scattered electron. It's all about the angle here. Which angle is correct? All right. So to figure this one out, it's all about conservation of momentum, right? So if I can find out what the momentum of the photon is before, and then that conservation the momentum has to be conserved, so I can use that with the momentum of the scattered photon, because I got these wavelengths here, I can use them. And then I can figure out what does the electron have, and then determine the angle of that electron. I want to predict it's going to be one of these smaller angles, but I don't know, honestly. I don't think it's going to be this A one. Okay, so what I would do is determine the initial, right? So we have, so that's the initial momentum. That momentum is going to be X and Y, but it's all Y at this point, right? It's going straight up, and that's the sum, because there's only one thing that's happening beforehand. Then afterwards, let's change the size of this back, cut it down. After the collision, this photon now goes this way, downwards, with a momentum, and at an angle, and that momentum is going to have an x and a y to it, at an angle of 43 degrees, right? Because it's 133, I'm just going to minus the top 90 off it, so 43 degrees. And then my electron is going to go somewhere in this direction. That's what we're trying to find at this point, right? Don't necessarily know. We want to know the angle up here. What is that angle? Okay. So we need to find the x and y. If I know the x and y, I can find that angle. Okay. So the reason I didn't quite do that, because I have this number in my calculator. This is the wavelength with all the decimals of the final one. So I'm going to use that to calculate this momentum afterwards using h over lambda. So 6.63 times 10 to the negative 34 divided by this answer. So this is going to be 4.7271 times 10 to the negative 23 Newton seconds. Okay. And then I'm going to use trigonometry to figure out the x and the y components of this. I kind of like how the y is like the opposite direction here. So based on a sign, I should put a sign convention here too. Positive, positive. This y is going to be negative. This x is going to be positive. This x looks like it's negative, and this y is going to be positive, but that's a totally different story. This should kind of just work itself out here. So I'm going to do the y first. So sine times sine 43. Again, making sure your calculator's in the right mode. Can't believe it. I hope that person didn't need to be in the right mode when they did their test. Ooh. Hope not. And then over here, you're just going to divide. Yeah, back to that number. And then I'm going to do cos for the other one. So times cos 43. And approximately the same, but not exact. Okay, this again, Newton seconds. Okay, based on our logic, since x has to add up to 0, this has to be the same as the other x, but in the opposite direction to make sure it adds up. Okay. Not too bad. And then the y's, they just had to add up to what the y is originally. So they give us, well, I had to find out the wavelength was. So there's the wavelength. So h over the wavelength gives me 6.666666666. Let me just put that here. Again, I just want h over lambda. This is my initial. To find that initial there. 6.6 repeating times 10 to the negative 23. You can see that the momentum did go down, so that true statement up there before. And this is all in the y direction. So there we go. So what we do, we have to figure out what two numbers over here would add up to this y that we have on this side. So I got this number, I'm going to add on. I'm going to run out of decimals here because I didn't write all the decimals over here for my y, but I'm going to get a good approximation here. It's going to be 9.8906-ish times 10 to the negative 23 seconds. Okay, so now we know what the picture looks like. There's lots of y and a little bit of that, so 45 degrees doesn't make too much sense here. So I know it's probably not going to be A or C, but I have to know if it's at 19 or 24. So I do my trig. So I'm going to go tan inverse to find out what theta is. And I'm going to, you have to be very careful which one you're going to put on top of which. Oh, poop, I kind of scrolled here really far away from where I should be. Poop, yeah, there it is. Oop, it's close. Okay, so my picture, I'm trying to find this angle that's on the top here. So my opposite is my y, or so my x. Why did I do that? My opposite is usually y. My opposite is my x. My adjacent is my y. So in my picture, I'm down here. That means I'm going to have to put in here the 3.4572 number in the top and the 9.8906 on the bottom. So tan inverse 3.4572 divided by 9.8906. Get 19 degrees. Which is that one? So it's got to be B. There you go. It's a lot of work, right? But you get it done. You got lots of time. You might as well take your time, right? What else are you going to do in the day? The test and stuff. Explanations. Einstein's explanation of the photoelectric effect requires light to travel in little bundles. That's true. And that is a particle thing. Okay. Young's experiment, double slit, requires light to interfere with each other. Waves interfere. So that's a wave one, right? So this one is, that's a particle. Oh, my thing's all messed up here. Particle. And then interfere, that's a wave. De Broglie requires electrons to exist as waves. This is wave-particle duality, right? Electrons exist as standing waves and other waves. So this is wave-particle duality. So this is okay. So based on like having both wave and particle behaviors there. So it's both of them. A group of students, well, it was an hour in. A group of students produced the following observations related to the photoelectric effect for light that's incident on a surface. Light that is a frequency less than the threshold will not result regardless of the intensity. That is true. So that is the particle. Right? This is quantum. This is the quantum world, right? For light that has a frequency higher than the threshold frequency, more intense light produces more electrons than less intense light. What is classical theory here? What are you supposed to do? So I can't explain. Yeah, it doesn't explain one. Like that's only quantum ideas. Like the wave theory said that no matter how long, if you just put it on long enough, something will pop out, right? So, so I don't like this one, and I don't like this one. So it's got to be 2 and 3. Yeah, so I guess that could be both, right? It's more quantum than anything. Intensity of light has no effect on the kinetic energy that's emitted by the surface. According to that, like that doesn't work because intensity of light. Yeah, so I'd say it's 2 only. That's my guess. I don't like that question. It's just it's a weird thinker. The intensity of the light has no effect on the kinetic energy, but according to the classical theory, if I put more light on it, they're going to kind of build up onto each other and pop out electrons faster. Right? It's just kind of they think of the amplitude is the intensity, but not. Right? It's just a weird thing. So yeah, I'd say it's B only. I don't know if that's the proper answer there. Inelastic, most like inelastic and kinetic energy is not conserved. That's probably going to be the case, but we can double check that based on line of best fit. What is the speed after the collision, and based on line of best fit, what's the combined mass is whatever. Yeah. So what they're trying to do here is they're trying to make you just avoid at 6 centimeters, because there's a dot there, then you're just reading what that number is, because the line of best fit doesn't go through that dot, right? So they just want to make sure you can draw a line of best fit properly and actually figure out where it actually crosses there. And then we're going to use the slope to actually figure that out. So what I'm going to do is I'm going to plot this. But I'm going to try to plot it as accurately as possible. That's why we have calculators. Everyone should have a calculator here. And we're going to go through this. I don't have to worry about my thing. So I'm just going to go stat edit. And then I'm just going to put the dots in as accurately as possible. You notice all these dots are pretty good. They're like halfways and they're either right on the intersections. So this one at the bottom here is, goes by 2, right? 2, 4, 6, 8, 10, yeah, 2. So this is 1.4 centimeters per second. They're all going to be centimeters per second. I don't have to change that. 2.4. We're going to do all the x's first. 3.2. This is 2, 4, 3, 4.3, 5.4, right at 6, that's the one we're looking for, and 6.4 is the last one. Okay. And then I'm going to do all of the y values. So this goes up by ones, I believe. 1, 2, 3, 4, yeah. So 1, 2, 3, 4, so 0.4, okay. 4, 0.9, so 1.15, that's halfway, 2.5, right? Well, 1.75, right? 2.3, so this is the 6, so this is what we're trying to trap you, saying put 2.4 down as the answer, but 2.4 is not going to be the answer. 3 is the last one there. And then I'm just going to turn on the plot. So go y is equal to, hit the plot, turn that one on the top there, and go zoom stat. All right. And the reason I do this to see what it looks like is just make sure it kind of looks like this picture. So I'm going to just go to my window here. I'm just going to put a 0 in both of these spots here. So the axes are right on the corner there. Yeah, that looks like it. You can see that lower dot there. That's the problem. That's what I'm trying to fix here. We're going to create a line of misfit. It doesn't go through 0, 0. So that's just interesting to know. That's probably why it's inelastic. And we're going to do a linear regression. We're going to store it. So I'm going to go alpha, trace. I'm going to get to that spot there. I'm going to go y1 and calculate. So there's the slope. We're going to need that later, but that's going to be right here. So we could just use that here. Here's the line. Looks pretty good, but you notice that line is higher than that dot there. So we're just trying to figure out at 6 centimeters. So I just go trace and I just type in 6. Oh, yeah, this is different now. You just type in 6 and hit enter, and I can just move my cursor over there. But you could just also go second calc value. Just make sure that you're on the right thing. You're not on the dots, because if you're on the dot, you're going to get the wrong answer. All right, actually, it doesn't let you do that. Good. So here it's actually 2.59. You only want 2 sig digs, right? A, B. So 2.6 would be our answer for that one, right? All right, so 2.6. 2.6. Now what we're going to do is we're going to use the slope, and there's a slope right there, but you can also go to y is equal to and find it. So my slope of my line is 0.485017859, etc. There's a lot of decimals here. All right, just a nice number. There's no scientific notation part to it. But what does it actually represent? All right, so this is one of these collision questions. Talk about speeds before and after. So a good equation for this would probably be conservation of momentum, right? So we have momentum before, and it has to be equal to the momentum after, right? So the momentum before, so this here is going to be 0, is just this initial cart, right? So I'm just going to go v before here. That's going to be my x variable, right? Yep, the cart one before. And what do we know about the cart before? We know its mass, 1.54. So we know that much. So 1.54 grams? Kilograms. It's big. Oh, it is kilograms. Okay. So we know its momentum is 1.54 whatever x is. The reason I put an x there is because that's my x variable, right? Plus 0. So the sum of all the momentum beforehand is just this 1.54x. Okay, we know that's going to be equal to what's on the other side. Now they're connected together here, with this new velocity afterwards. They're both together at this point. So we'll call that y, because that's my y variable. And my mass is the sum of these two pieces, right? So whatever these two things happen to be. We just don't know that second mass there. It's just kind of an unknown. Okay. And then our momentum is this plus, well, not plus, just this times its velocity. So this times y. So that means this momentum is equal to this momentum. Like that. Okay, so we can create a little equation down here. So 1.54x is equal to, and if you want to rearrange it, you don't have to necessarily do that. So we could just go 1.54 plus m times y. And if I rearrange this for y, this is my y variable, I get 1.54x divided by 1.54 plus m. So anything that's in front of my x must be my slope. Okay. So all that stuff that's in front of that's my slope. That's equal to this number up here. So I can rearrange this now, or actually just write it out, that this is equal to my slope. A bunch of decimals there. Okay, now what they're trying to find here, they're trying to find the combined mass. So they're not trying to find what the individual mass of that second car is. They're just trying to find out what this total mass on the bottom is here. So this combined mass. So what I'm going to do here is I'm just going to be, this is the combined mass. All right, that's what I want to find. So I'm going to rearrange this to get the combined by itself, which is going to be 1.54 divided by this slope number. So it's almost like twice as much. So I can just go over to the calculator now, and I'm going to go this is not going to work in here. 1.54 divided by this slope number. Now I could go just find it. There's a way to pull it out of the calculator, but it looks almost just easier to type it in here. So that's the two masses together. I could just subtract the other to find the mass of the other one if I wanted to, but here it looks like they just want 3, 2 as your answer. Ooh, okay. So I'm almost done the main part here. Now we just got these Venn diagram ones here to do. Got a few of them. So matching the numbers to the Venn diagram. So the measurable mass of the product is less, product is what's afterwards, yeah, is less than the measurable mass of in a spontaneous reaction. So they're kind of saying, does this happen spontaneously? The kinetic energy of the system increases in a spontaneous reaction. Yeah, so not being forced together here. That seems like, well, these ones are easy. So this one here at the bottom is this one's a fission reaction. So fission is 1. This one down here is an alpha decay. That's not fission or fusion. That's just its own thing. It's radiation. So you don't classify it that way. So that's 4. That's obvious. Now, these, the response, like what? Yeah, it's a tricky one. Let me see if I can find what I put down previously, because I did these keys before. The response number 10. Where did I put that? There it is. Yeah, so I put 3-3-1-4 or 3-1-1-4. So 3 is both. So yeah, it kind of makes sense in these reactions. The word spontaneous is kind of like Yeah, it's iffy. In these reactions, the mass will decrease, which makes sense, right? So that happens in both these. If the reaction is going to release energy, fission's spontaneous enough. And then the kinetic energy increases because of that. It just, those should go hand in hand. I don't know why I went 3-1. It just seems to make sense to go 3-3 as both of those. Okay. Gravitational fields. Okay, so can be directed towards the source. That's all of them, right? Oh, actually, I think they want it to be all of them. Yeah, because the north and south are like the sources, even though the source is technically the moving electron. But yeah, so here they can be directed towards the source. So like in gravity, the gravitational field is always towards the source, right? In a negative charge, the electrical field is towards the source, right? And if I had a north or south pole of a magnet, the field lines are directed towards the south pole, right? That's the south of a magnet, right? So yeah, they could be that. So this one here, though, gravity can't be directed away. It's always towards. But we can have a positive charge, which is away from the source. So that could be my electric field for that one. And I can have a north, which is directed away from that source, right? So I can have those two. So what would that be? That would be electric, so it would be 6 according to this thing, right? Inverse proportional to the square of the distance. So remember, E is directly proportional to 1 over r squared. G is proportional to 1 over r squared. But B, we don't have a formula for this. It's just 1 over r. So not proportional to the square. Right? So that would just be 5 here, because between gravity and electric. So 5. And directly proportional to the square, distance squared. That doesn't be same, right? That's none. So that's 8. Right. Means it would get stronger as you get further away, but that's not true. Okay. Didn't we do this question? Yeah, that question's done. Didn't we do this question? Yeah, that question's done. We're going to skip those 2 questions because those questions are repeats. Why do I have them again? I don't know. Yeah, they're just repeats. Okay, so let's check out this one here, numerical response number 6. Well, there's multiple 6s here, but whatever. Possible paths of the bubble chamber into the external magnetic field. Now, what we know about this is because of the number of the paths going upwards and the number going downwards, it just most likely the top ones are going to be positive and the bottom one here is going to be negative. Because there's more positive charges out there. Protons, alpha particles, positrons, right? So those are the kind of things you could have, but electrons are our negatives, right? Not too many negative things out there. So most likely, this will be our negative and this will be our positive, just because of how many there are, right? Most likely also S and W are a positron electron. So if this was an electron, this would be a positron. And then maybe this is a proton, and then maybe this is an alpha particle. Right? That's my guess of how it's going to work out, because this is more positive pieces. Right? The one that's going right down the middle, that could just be a neutron. It could be a gamma particle. It could be a neutron. It could be any neutral particle. Could be a neutron. So like that last one there, 7, seems like it could be true. And this could be done in any order, so I'm just going to put 7 as my last one. So that makes sense. That would be the last one. It looks like S and W could have the same mass, charge mass ratio. Not the same, they could have the same mass, maybe. Definitely S and W have the opposite charges. I'm going to put that down. So that's for sure. They have opposite charges, right? T and U definitely have the same charge, right? So the same nature, so that's definitely true. So I'm going to 4 down. T and U could have the same charge mass ratio based on their speeds. Like if they're all going the same speed, Doesn't specify if they all have the same speed, do they? Oh, identical velocities. So they all have the same speed. So because of that, that's out. And that's out. I don't know if they have the same... Actually, they could have the same charge mass. Maybe. Maybe. But there's no way to know. Right? You'd have to know the charge as well to figure that out. This one could be maybe, most likely they are, but they have the same charge to mass ratio for sure. All right, because they have the same radius, they're going the same speed, and you calculate that. So remember to find that charge to mass ratio, we say Fm is equal to Fc, we go QVB is equal to M AC, and then I'll just go mv squared over r. We'll cross off one of those v's, and we're going to go q over m, and then this is going to be v over br, right? So it's dependent, the charge mass ratio is dependent on the speed, which they're both the same, right? Same. And the r changes. If the r changes, they have a different radius, they'll have a different charge mass ratio. If they have the same R, like S and W, then they must have the same charge mass ratio. So 2, 3, 4. Ah, there's the key right there. You know, this is multiple answers here. Okay. There's lots of questions here. Cool. All right. I might finish off these other ones later. I might talk about them tomorrow during the help session because these kind of questions could pop up, and maybe we'll do 1 or 2 of these in class, and then maybe I'll finish them off. But I'll do these last 2 for sure. All right? In a copper sheet, pull through this. These are easy ones because there's just the hand rules. Copper sheets pull through which edge will become relatively negative. So they're talking about like which way the electrons are going to be forced here. So we're going to use our hand rule again. So from north to south, there's my magnetic field line. This is the direction the electrons are moving, and we're just trying to find the force. So we pull out our left hand because we want to know which way the electrons are going. And these are negatively charged, right? So these are electrons. We put a thumb in the direction and that way. So we put a thumb into the page or hand down. So my left hand kind of looks like this. This is my thumb right here. These are my fingernails. This is the top of my hand. It's kind of ugly, isn't it? Okay, so my thumb is going into the page, but my force is going downwards, right? So this is the direction of the magnetic field. The thumb is in the direction of the field. So because I did that, my thumb is going down, or my palm is going downwards, north to south. Yeah, down. So if that's the case, the electrons are going to move towards the bottom of that sheet there. This one here, to induce electron flow in the direction, so that they want the direction here. They want the electrons to go this way. So that means we have to force them that way. So we have to create a force that way. We have the magnetic field going this way. So we had to figure out which way we're going to move the whole wire. So that's where I got to figure out where my thumb is. So in this case, I got to put my palm into the page, fingers from north to south. It looks like, because I have my hand, so this is what my hand looks like here. Oh, that's weird. How many fingers do I have here? There's my fingernails on the top here. There's my thumb. This is the top of my hand. So the reason I did that, because this is the direction of my magnetic field, right? I put my palm in the direction of the force. That's a 3-dimensional arrow there, so if you can imagine that. And my thumb is the direction we have to move. So we're going to have to move this thing downwards to number 5 there. Did I put that down? What are my answer keys? If I just go up here, did I put that there? What, 80? Is that the right one? No, that's not the right one. Oh, why did I put A? Maybe I did put the wrong one there. Yeah, it is definitely D on the bottom here. Let me just double check what I did here. So my hand that way into the page. Yeah, it's definitely going to 5. So 5. And this way, my fingers go that way. Thumb that way. Because that's the direction that all the electrons are moving. And my palm goes down. So it'd be C. Yeah, it's definitely not towards us. Yeah, so this is definitely C. Not A. North is south. Yeah, okay, there we go. Cool. All right, I'll see you tomorrow. Bye.